Hello, so in this video we're going to talk about this idea called smooth functions. Now a smooth function is really important in linear programming and non-linear programming because it makes our job a lot easier if the function is smooth. So being able to identify if a function is smooth, or maybe just introducing something that to make the function smooth, makes our job a lot easier. So what does a smooth function actually mean? Well, the first thing that it means is that it has to be continuous. Okay, so what does continuous mean? Well, continuous means that you can draw the function. You can draw the function without taking your pen off the paper. So it might be something really complex. Okay, but as long as you can take the function, as long as you don't take your pen off, you can draw the function without taking your pen off the paper. Then it's what's known as continuous. So this would be an example of a discontinuous function. So that's a function that you do have to take your pen off the paper. So you go like that, and then you go like that, okay? And then you might go like that again, okay? So, for example, that's a discontinuous function. I know that's a bit contrived, but basically you have to take your pen off the paper. So you might have jumps or you might have holes in the functions. That would be discontinuous. But continuous functions is just basically is part of being smooth, okay? And that kind of makes sense, yeah? If it's smooth, you can draw it smoothly, okay? You don't have to take your pen off the paper. The other part of it, the other half of it, is that it's differentiable at every single point. Okay, so it's at least once differentiable at every single point. So that's fairly kind of self-explanatory, right? You can, at every single x value point, so at every single point, you can differentiate it. Okay, and fairly obviously, that this is very useful. This is more the property that we're interested in linear programming or non-linear programming. Because we deal a lot with derivatives, when we want to try and maximise or minimise a function, we do that by taking its derivative instead of it equals zero. In other words, we're finding the stationary point, right? So, it being differentiable makes our job a lot easier, right? However, so, you can check this. The easy way to check this is by drawing it. So you can check it's continuous by drawing it. You can check it's differentiable by checking the property that the limit from above satisfies the limit from below. So what is the formula for the limit? Well, it's the limit as h approaches 0, okay, from the positive direction of f of x plus h minus f of x all over h, okay, and the limit from above, so the positive direction, must equal the limit from below. So what do I mean by that? Well, let's say this is the point we're approaching. We've got a function that looks like this. Okay, well, if we're approaching from below, we're approaching from the negative direction. This is going to be from below, so we're approaching along this direction. We're travelling along the curve from this direction, travelling towards this point here. Okay, and if we're approaching from the right, this will be approaching from the positive direction. So in other words, we're travelling along this curve from the right direction. So we're travelling to the same point, just from two different directions. Okay, and if the value from the left is equal to the value from the right, so let me take the limit. So if we approach the same value from the left as the same value from the right, then it's differentiable. Okay, so this, for example, wouldn't be differentiable. Don't know whether I'm going to... There we go. So, for example, this wouldn't be differentiable because fairly obviously, if we now approach from the right, so we're approaching from this direction here, we're going to approach a different values to when we approach from the left. Okay, so that's kind of fairly self-explanatory. So now let's talk about this idea of usable derivatives then. So in other words, okay, if a function is smooth, okay, so in other words, there do tend to exist derivatives. Remember the reason why we take derivatives, because of course we want to find stationary points, right? So if the derivative exists, okay, then basically the idea is that we want to set the derivatives, all of the derivatives, so I'm going to denote all of the derivatives by this. Okay, and we want to set them equal to 0 because, of course, this is what's known as the grad operator or the gradient operator, and it's like a vector, and it's the vector of all the possible, all the possible things, all the possible directions. So, derivative of f with respect to x1, derivative of f with respect to x2, and so on. So all of the possible derivatives which we can possibly have, and we set them so that all the possible derivatives with respect to all of the individual variables that we can possibly have, okay, and then we set them equal to 0, because that's going to give us our stationary point, right? We set derivatives equal to 0, it's the point where the function isn't changing. And that's going to give us our derivative, that's going to give us our stationary point, okay? Now, if we can't find the derivative easily, so if we can't find, these derivatives very easily, then we can use kind of computational methods to find derivatives, and that's okay, although sometimes they can be really horrible functions and they take a long time to compute. They can take a long time to compute the derivatives, in which case, By the way, all the derivatives, all the methods that we look at in this course will be involving derivatives, so we will be using derivatives in some way to try and find the maximum or minimum point. Now, if we can't find the derivatives very easily, then we can use computational methods to try and find out what these derivatives are. However, that may take a long time. It may take a lot of computing power and actually may end up being more expensive and may end up being more cost to us than actually just making a guess. Okay, we may as well have not bothered we may as well not bothered solving the problem in the first place. It's not that valuable to us. It's not that important to us. In other words, to try and calculate what these derivatives are would cost more than not kind of bother computing it in the first place. So in other words, we don't have to bother trying to solve the optimization problem because it will actually cost more than trying to find these derivatives. Okay, so that might be one. We can use the search methods, but it may be sometimes more complicated. Now, what happens if the derivatives don't exist? So in other words, it's not a smooth function. Okay. Well, then basically what we need to do is we need to construct what the derivatives look like. And these are the methods that we're going to start looking at in this course. Okay. So actually, the next video we're going to start looking at the one-dimensional search. So the one-dimensional search, fairly obviously, the one-dimensional search is basically just a left and right search. So one dimension is basically just a movement in one direction. Okay, so if you like, it's a flat plane. Okay, and we can only move left or right. We can't move up or down, right, or back and forwards. We can only move left or right. So that's the one-dimensional case. We have to if the derivative doesn't exist, then we have to construct an approximation for it. And the first thing that we're going to start looking at is the approximation in the one-dimensional case. So in other words, just a straight line. Okay, and the first thing we're going to look at is the golden section search, and then we're going to go on and look at something called the quadratic fit search. Okay, quadratic fit search. And then the second thing that we're going to look at is the multidimensional case. And that's called the Nelson-Mead method, right? So basically, we're going to start now looking at the case where the derivatives don't exist, right? If the derivatives don't exist, then we have to construct an approximation for the derivatives. And the one-dimensional case that we're going to look at these two methods. And the multidimensional case, we're going to look at something called the Nelson-Mead method. Okay.